Yeah, the 28 is a perfect number, and I doubt if I can give a perfect lecture, but I do have a lot of good stories to tell, so I'll do my best for you to understand. And I guess the first thing I should say is the big news. That is, those of you who wish to give Christmas presents, yesterday I sent the insides of this book to my publisher, and so it's possible now to order copies. I don't think they'll have them printed by Christmas, but at least they have the cover design, and the official publication date I think is February 3rd. But inside the book it says printed in January. But anyway, I'm quite happy that this book. Well, I had lots of people helping me, and I worked on this for the last 5 years. It was my main project. So it's called Constraint Satisfaction, and that means that if you have constraints, you have satisfaction. Now, next thing is the title of my talk today was Strong Components and Weak Components, and everything that I don't cover today or that I get wrong is spelled out better in this pre-fascicle 12a. So I mean, this is volume 4, fascicle 7. The first fascicles became published in hardcover as volume 4a and volume 4b. This is going to be the first third of volume 4c. And then if I live long enough, this is going to be someday fascicle 12, or the first part of fascicle 12. Who knows how long the force will be with me, but anyway, I'm going to keep telling these stories as well as I can. So the full story is here, and you can find it on the web. And afterwards, I'm going to put on my website links to it, so it's easy for you to get it. And there's also some computer programs that I'm going to talk about, and those I'll put links to all that stuff on my website afterward. Now the strong components and weak components are described in this, and I guess I should mention, I don't know, I'm going to see if Ronnie can zoom in on this footnote here. But there's a subtitle to this lecture, and that is, which algorithm do you love the most? And so I don't know. I guess I can zoom anyway. Okay, so here it says, over the years I've often been asked, what is your favorite algorithm? Immediately I think of how I hate to be asked to choose favorites. But then I realized in this particular case the answer is clear. Tarjan's algorithm for strong components is without doubt the algorithm that I love best. When I learned of this elegant procedure in 1973, I understood for the first time that data structures can also be deep. So the topic really is it's not only an algorithm, but it's data structure. The way that we can organize the representation of the graphs that we're dealing with, and that we're getting these. We're going to figure out what the components of a graph are, and it's amazing how beautifully everything fits together, because every time the computer needs to make a decision or to figure out something, the information is right there at its fingertips, and it hardly has to. I mean, it doesn't have to go over and do anything twice. It's always doing two things at once. So I hope you can see that here we have a case where it's not just the algorithm that's interesting, but the way the algorithm is represented inside a computer that makes this one special. And you know, I knew that theorems can be deep. I knew that algorithms can be very, very profound, but this goes further. It says also the data structure in an algorithm can have really non-trivial ideas in it. Okay, so now what are strong components and weak components? I might as well explain that. I hope you know what a directed graph is. A directed graph is a bunch of points connected by arrows, and for every ordered pair, for certain ordered pair of points, we'll, like U and V, we'll have an arrow between U and V. So here, for example, is a directed graph, and it's got well, I don't. 1, 2, 3, I don't know, about something like 16, 17 vertices, and then we've got an arrow here and there, and we say that two vertices are in the same strong component if you can get from one to the other. I mean, you can get from U to V and back again. So I put little dots around the strong components here. These three vertices are in the same strong component because they can go from here to here to here, so and from here back to here again. These three here, we have a cycle. Certainly, if you have a cycle of n vertices, all of them are in the same strong component. And but here's a case where there's only one vertex in the strong component by itself. There's lots of things can get to it, but it can't get to anything else. So that's the idea of a strong component. Now, what about a weak component? And here the story is a little bit unfortunate because because there's a lot of papers had been written where people said a weak component is just whether you can get from one to another without looking at the arrows. You can go either direction, in which case this thing would all be one weak component. But that spoils the. So we should call that an undirected component of a graph rather than a weak component. But what a weak component is a much more interesting and useful concept, these vertical lines divide this thing into weak components. So I think the best way to think of it is suppose we, everything in this weak component can get to everything in the other three. And everything in this one can get to everything to its, so this guy can get here, but nothing in this component can get back on the other side of the line. So if we shrink a strong component to a single point, then we get a graph that has no cycles in it, no loops. Imagine that all these circles we just made, that one supervertex. So that gives us an acyclic graph, a graph that has no cycles. But now suppose we shrink all the weak components together, then we get a straight line. 1, 2, 3, 4, or 0, 1, 2, 3. So that's the idea. It's the most general partition which has this property that gives you a straight line. So people who like the phrase partial order says shrink the strong components, you get a partial order. Shrink the weak components, you get a total order or a linear order. And that's a nice concept. Now, I'm glad to say I looked it up on Wikipedia, and for the last 2 years, thanks to David Epstein, there's been a good article on Wikipedia about weak components. But before that, you would have been. I was very disappointed at what Wikipedia said about weak components. Although his article is excellent, except it could use some illustration. So maybe maybe next week somebody will improve it by adding a picture to it. But anyway, that's what I think mathematically deserves to be called weak component, and the history is both interesting and unfortunate in a way. The idea of weak components was invented by Professor Motzkin while he and Ron Graham and I were in correspondence about another problem. And here's a letter that I got from Motzkin. It's dated 1970, February 28th of 1970, from Motzkin to Ron Graham, and he says in here he'll say something like, for arbitrary R, this is how you get a total order when you have this partition. Now, so Ron and I were working on this problem, and in December of that year, 1970, I wrote to Ron and I said, I got to look at this problem again yesterday. It turns out that each member of you, me, and Motzkin took a different approach and proved something that is more general in some sense than what the other two proved. So I showed one thing, Ron showed another thing, and Motzkin showed this thing about weak component. So anyway, here it says, I couldn't have proved this without Motzkin's results, so I resolved last night to include him as joint author. Then, this morning, I received the unfortunate news of his sudden death on Tuesday due to a heart attack. So that's why I said it's a sad story, too. So this paper was published shortly after Motzkin's death. And it came out in this journal, Discrete Mathematics, I think it was volume 2, number 1. And so here's the article about, and in that article they have a picture, actually, which you might recognize if you turn it this way. Okay. So, okay. Now, that was 1972 when Discrete Mathematics was just starting its second volume. By now, I think it's in volume 1,000 or so. Its volumes now have thousands of pages. Nobody had, in their wildest dreams, believed in 1972 how many excellent papers would eventually be written in that journal, Discrete Mathematics. Similarly, Bob Tarjan's algorithm for strong components came out not in volume 2, number 1, but in volume 1, number 2 of Siam Journal on Computing. So this was again 1972, and the beginning of a huge, wonderful tradition of papers when these journals were just getting started, and nobody really had any idea how rich. You have a question?
Can you look at the directed graph?
Can I what?
Can you look at the directed graph on the projector?
The previous thing, John.
I'm Zoom.
Go back to the graph.
Just pick a directed graph.
Example.
The example of
I'm sorry?
Just want to see this. Yep, just pick that. Yeah.
Oh, okay.
From what I know, weakly equivalence is, weak components are when they're strongly equivalent or they're uncomparable. So there's an arrow from the top strong component to the second strong component in the first section on top. Yeah, that one to the one.
Right. So anyway, if they're incomparable, then they have to be in the same week.
This from the top one to the one on the one up there.
let's come down.
I tell you what, I'm gonna put names on all these. In fact, each way I give names makes the algorithm a little bit different. So I'm going to put sort of random numbers in here.
Yeah, so from M to O, there's an arrow.
Okay, but okay. So now E. Anyway, so I'm giving it the letters A through O. And this is, I used a random number generator. Actually, I have the cutest random number generator. It's little marbles inside of a pen, and you can shake the pen, and then the marbles go down into a tube, and you can see what it looks like. Anyway, that's how I got this ordering. Now, your question is.
So there's an arrow from M to O, so why are they the same?
There's an arrow from N to O?
Yeah.
No, it's
M to O. So why are they
M to O, yes.
Yeah. So why are they part of the same component?
It's because M is incomparable with G and G is incomparable with O.
Oh.
And so by transitivity, so it's an equivalence relation. And so if you have a chain of incomparability, then they're in the same weak component.
Okay.
I might as well mention now that there's this wonderful idea called topological sorting. So if you have a graph that has no cycles, then the topological sorting, you write the super vertices like the strong component. You write them in such a way that all the arrows are going to all the arrows are going the same direction. So one topological sorting would be like A, O, G, N, F, J, P, T. But there are other topological sortings too. I could start with this one, and then I could go here. I could go here first, and well, I guess I got to do after O. Well, anyway. You choose a source, and then you throw it away, and you choose another source. Okay. Now, if you look at all the if you look at all the topological sortings, if X is always in front of Y in all of them, then they're in different weak components. But if some of them have X before Y and some of them have Y before X, then they're in the same weak component. So okay. So, now. Going back to the history of it, Bob Tarjan published his algorithm in the first volume of Sam Journal of Computing, and this is number 6 on his list of publications. He was a grad student at the time, and I read it at the end of in January of 1973. I looked at my diary, and and the previous week I had written this novelette called Surreal Numbers, and then on Monday I came back to work, and I started looking at this journal, and I found this algorithm and decided I loved it. Okay, now and so the algorithm, it's one of 2 algorithms here, and he's got explained there and so on, and it's not exactly the algorithm we've improved it over the years, but I did want to show you this, which was the math review that came out of the algorithm. It says the author first describes the algorithm for finding strongly connected components, and he says this algorithm it takes linear time, and it's not very surprising. So the reviewer was not at all impressed with it, and so there's no accounting for taste, but I do hope that by the time I finish today, you'll get some idea why I like it. Okay, now let's see what's next. Yeah. How are we doing on time? Okay, I want to spend a certain, like I want to spend like 45, well, let's see, we've already used almost 10 minutes. So anyway, let's try to go 35, 15 or something, 35 on strong components and 15 on weak components or something like that. That's what I'll try to shoot for. The algorithm was very well described in the first great textbook on algorithms by Aho, Hopcroft, and Ullman. John Hopcroft actually was part of the invention of this algorithm. John came out to Stanford for his sabbatical year, and well, we didn't have that much office space, so he shared an office with Bob Tarjan. Bob was a grad student, and John was our visitor from Cornell, and they got to talking, and they invented all kinds of beautiful algorithms, and John especially had a good algorithm for finding not the strong components of a directed graph, but the bi-connected components of an undirected graph, and then he showed that to Tarjan, and Tarjan said, "Oh yeah, hey, we can use a similar idea for strong components," and then and you know the rest is history. So and so they have a good description in here of Tarjan's algorithm, which is, as I say, it's subtle. It takes a while. It takes a while to get it. I'm not going to be able to explain it so that you just understand. But if you have time to look at it and realize why it wasn't, why it's not trivial, then some of my goal will be achieved. This book came out later in the 50s by Shimon Evan, who went to Cornell and worked with Bob in the early 70s. And let's see if I can where does he describe Bob's algorithm? He had this very nice idea. Let's see where trees. Here we go. Strong components 64. Anyway, it says the algorithm involves something that in this book is called the low point, and he says it seems like a circular situation. In order to compute the low point, we need to identify the components, and in order to find the components, we need the low point. However, Tarjan found a way out, and that's the reference to the subtlety of this method. So best way I know to explain it is to try to go through and again ask me questions if you want clarification. Now I'm going to I'm going to imagine that we're given this directed graph, and we want to figure out its strong component, and so I'm going to write down the edges of the graph quickly here: A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. That's enough. Okay, now, so I just have to put all the arcs. So A, here's one from A to M, and then there's one from M to A, and then there's D to M, and M to D. M to O, right? Okay. Okay, O to N, O to B, O to F. N goes to J. J goes to L and P. B. This is a B. Okay, let's see. B doesn't go to anything. G goes to K. K goes to H. H goes to G and C. Okay. C goes to F. And F goes to L and C. It matters which one I put first. I mean, the algorithm is going to find the strong components in either case, but it's going to behave differently because the computer only sees this list. It doesn't have a picture of the thing. The computer is sort of going blind. And the best way, I think, to think of it, E goes to I and I goes to itself, so I goes to I. Okay, now I think that's it. Did I miss anything? K to N. N, okay. I'm glad somebody, I'd like to say I did that on purpose, but just to see, but the fact is I missed it, okay. All right, now, so I think it's a good idea to imagine that you're playing an adventure game. You're in a cave, and this cave has different rooms, A, B, C, up to O, and from each room you have different rooms you can move to, and so we want to explore this cave and find out what its strong components are. Okay, and in general. The algorithm that we're going to use is called depth-first search, which is a good way to explore any cave or any graph height.
I think L to J is missing. It probably has to come before the E.
L to I, L to J, right, and L to E. Very good. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23. Yes, I remember that was the number. Very good. Okay. Now, so we're going to try to do like any good spelunker exploring a cave, but well, the computer. It's only given these lists, and it has to try to visualize everything just given this data. Now, but inside the computer, I imagine that that each vertex that this is a linear list, like A first, and then B, then C, and so on. And then for each vertex in this linear list of vertices. Has a list of arcs going out, and this can be stored in different ways. But I'm going to say that the first thing I do is I have to get in the cave somewhere. So I look at the largest vertex, and I'm going to go all the way. So I'm going to first look at O, and I'm going to say, so I'm going to start exploring the cave at O, and this method is called depth-first search, and so the idea is we imagine that we're sitting somewhere in the cave. I'm sitting at position O, and I look at the next outlet from O that I haven't looked at yet before. So the first one is N, and so from O I go to N. Okay, and now I'm in N, and from N I go to J. Oh, sorry, better underline it. Watch me that I underline it. From J I go to L. This can be boring unless something new happens. Yeah, here's something new. From L it says go to J, and you say, oh, I've been to J before. So you know this. When you're in a cave, you can leave some kind of a litter behind or something, so that you know that you've been there before. So from L to J, we're going to I'm going to put this as a dotted line. I won't bother to write the arrowhead. Now, when we do a depth first search, there are five kinds of arcs, and so they're called a tree arc. Can you see what I wrote? Tree arc, a back arc, and there are three other kinds we're going to get to. So the tree arc, we have ON, NJ, and JL, and then the back arc was LJ. All right. Now, so LJ is done. Next is LE. So here comes E. So that's a tree arc. And from E, this said I, believe it or not. So we got from E to I is another tree arc. I goes to I. Here's a new kind of arc. It's called a loop. Okay, so I is a loop. It's not loops don't do anything for strong components. It doesn't change reachability at all. You could remove all the loops and then you still get the same strong components. But anyway, you do run into them sometimes. So here was the loop, and now E to I. Okay, now what next? I'm still at I, and but I finished with I, so nothing more to see from I. So at this point, since there's nothing coming out of I, I'm going to declare that I is a strong component. You've got a question, huh?
What about underlining JL?
What about underlining JL? Very good. LE, yeah, okay. So anyway, so I'm going to make clear this is a strong component. Got it. Now, and I go back, I unwind to the previous thing on the tree. How did I get here? To I, and so here's something you can't do in your adventure game. Sometimes you can't to get from one to another, you fall off a hill. You can't unfall off a cliff. So, but the computer can. So we go back to E, and E. We're also done with E. So well, let's declare that to be a strong component as well. Now L. We've seen J, but whoops! I've also I forgot. So I'm done with L as well, but I'm not going to declare this to be a strong component because I know that I can get out of it, right? So one important thing is, maybe the most important thing is that when we shrink all the strong components to a point, we got a graph with no cycles, and it's called directed acyclic graph, DAG, D-A-G, and in that case you always have sinks. That means that there's some, if there's no cycle and it's a finite graph, then eventually you get to something that has no escape. A black hole, you can't get out, you can't get out of it. So so E was a sink, and so I could take it out of the graph. If you take it out of the graph, then the remaining problem is to find the strong components on the remaining graph, and so eventually the strong components we're going to remove one sink strong component at a time, and until we've removed everything. Okay, so but now L is not but L by itself has branches out of it, so it's not a sink. I go back to J, but J, I haven't seen anything else. So any way out. So I can declare that J and L is a strong component. Wait a minute. I'm sorry. Oh, whoops. I'm sorry. J, I still have to explore to B here. And then B is going to be a strong component. B is a strong component. Now I can come back and I can declare J to be a strong. Okay, so right. In fact, I have to get a sink. I remove this sink. I remove this sink. There's only one sink left, and so I got to remove this sink next. Okay, and then JL is going to go away. All right. So let's see. JB was a tree arc.
One question.
Yeah.
How does the algorithm now know that L and J are a component? Is there a stack that it maintains?
So you see, I proved that it's a sink because there's nothing. It doesn't go to anything. I mean, the computer has to know at this point. I've drawn it here, and I'm using clairvoyance. Tarjan's secret sauce is going to tell us how to really do this.
But what I mean is, how does it know which vertices belong to it? Does it have a stack of the ones that so L would be on the stack or something?
What I actually have in the algorithm is a stack of all the stuff that I haven't put a box around, and that stack has things linked together. Right, you're right. And the two top things on the stack are L and J, and and somehow I'm going to know that nothing, neither L nor J, has an outlet. Yeah, but I'm glad because that's exactly the point that we're trying to get. Okay, so anyway, I think I'm done with J now. And so I go back to N, and N is done. So O is next is B, but O goes to B. This is a new kind of arc. It's called a forward arc. OB. And then OF, that's new. So OF comes over here. And F goes to C. OF is a tree arc, and then F to C is a tree arc. And C to F is a back arc. And then F to L is the next one, but FL goes to one of the strong components that we have already removed from the graph. We call those guys settled. So this is called a cross arc, and that's the fifth kind of arc here. So, it's not in the tree. It doesn't go backward to an ancestor. It doesn't go forward to a descendant. It goes across to somebody who's neither ancestor nor descendant. And so, well, we're almost done. So I might as well finish it. So C. Goes back to F, and then F went to C, and then L, and so now we're done with F, and then O is done. So I'm all done, and I've got this tree, but I haven't seen the whole graph yet. So I started at O. Now there's another way to get into the cave. That's not reachable from O. And so I go back, and so O is all finished, N is all finished. Next, I do M. So I start a new tree with M. And M then is going to go to A. And A comes back to M. And then M goes to D. So M goes to D, and then D goes back to M. so these, and when I get back to M, I'm sorry, M still has to go to O, but O is a cross arc. So at this point, I'm going to declare MAD to be a strong component. Interesting, because I wasn't supposed to be able to do that, because it leads to O, so what happened? Oh, I see. I forgot to declare these guys. I should have declared F and C and N and then O. Okay, so I forgot. Okay, so yeah, because I'm not a computer, I'm a human being. Okay, now so we've done M, A, D, O, and going back, H is still haven't seen H.
K still has an N?
What?
K still has an N?
K.
K has an arc to N?
K is out there. Very good. K is out there. I see that this is not an underline under the H. It's the upper line of a J. Okay, so K goes to H, right, and H goes to G, which we've seen. No, which we haven't seen, and G goes to K. Yeah, okay, so K goes to H, H goes to G, G goes to. This is a back arc that goes not to your parent but to your grandparent. Right. So now this object here is in general it's called the depth-first forest. A forest is a bunch of trees. And most years my Christmas lecture has something to do with trees, and again this year I got Christmas trees coming in here. So the depth-first forest in this case has three trees. One of them is rooted at O, another one at M, and another one at K. And in generally, if I had given different names to these guys, or put these in different order, then I would have got a different depth-first forest. But each ordering defines a depth-first forest, which you can prove things about, and each depth-first forest has its tree arcs and back arcs and so on, and a lot of algorithms can be based on the properties of this kind of arc. Okay, question? Yeah.
Since the forward arc and cross arc, they are.
The forward what?
We don't need to distinguish between the two.
How do I distinguish what?
Cross arc.
A cross arc?
Yes, because basically when we see
Every
cross arc, we do nothing.
So I don't just a cross arc is just one that it's not a tree arc, and it doesn't go to an ancestor or a descendant. So like F to L, L is not an ancestor of F or a descendant of F. They're both descendants of O. They have a common ancestor, but they might not even have a common ancestor. So.
But whether or not F and L are ancestors for each other, it doesn't matter for this algorithm. So if we see O points to D,
Yeah.
or if we see F points to L, that doesn't affect the flow. Yeah.
It doesn't affect the strong components, but it might affect the order in which we discover them. Yeah, but one great point is that we are always going to discover a sink component. So every time we discover a strong component, it's a sink of everything that's left. And then we say that's settled, and we remove it from the graph, and then we look for the next sink. So it goes, remove, and this means we're getting a topological sort of the whole thing, because because it always ends with a sink and then another sink. So this algorithm not only finds the strong components, it also topologically sorts the strong components. The beauty of it is that it's so darn fast. So in the worst case, if you have m arcs and n vertices, it's 5m plus 17n accesses to memory. I mean, this is the number of times you fetch or store during the algorithm. At most 5 for every arc in the graph, and at most 17 for every vertex in the graph. And that includes, all this stuff about looking to see if you're at the end and how far you are, and updating your point and all that. So it goes lickety split. All right, now I'm going to talk about weak components, and then maybe I'll go back and do a little more about strong components, so you can see some of the subtlety. So guess who has the best algorithm for weak components? So in 1974, volume 3, number 1 of this journal, Information Processing Letter, this journal was set up to be something that would publish papers that are kind of short, and so he had an algorithm for weak components. For finding weak components, and so. 3-page paper, and I've scribbled a lot on here, but anyway, it's all explained now in my fascicle 12A, and so how are we going to identify the weak components? And there's a beautiful way to simplify it. So here I've shown a case where imagine that there are 10 strong components. I numbered them 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this numbering is in a topological order. That means that every time there's an arc from one to another, it goes from a smaller numbered component to a larger numbered component. And this particular case has 3 weak components, and I'm going to try to explain, like in answer to your question, why 0, 1, and 2 are in the same one. But so because 0 is incomparable to 2 and 1 is incomparable to 2. But okay. The idea is if we look at each weak component one at a time. It's an acyclic directed graph, so it has sources and sinks. I put an S for a source and T for a sink. Can you see that? So here, S, T, and this is S and T. So 2, as far as this is concerned, 2 is both a source and a sink in this little graph of 0, 1, 2. T is a sink, but it's not a source because 0 comes to 1. 0 is certainly a source. There's nothing in front of that, and 0 is not a sink because 0 is supposed to be it's not a sink because it goes to 9. So wait, why did I've got to be a little careful there. Okay. Well, maybe this is an error. I'll fix this if it's an error. I'll check it out. Okay. Each sort vertex within a component is marked with S, and each sink with T. So I think I should have called this well, anyway, the rule is that every sink in one weak component has to be connected to every source of the next component. Picture, you have a question? So anyway, 0 and 2, I'm sorry, 1 and 2, that's interesting. So every sink has to be connected to every source of the next guy. I might have to fix this diagram, I don't know. 0, yeah.
Maybe stupid. But could you explain what is a sink? And I just wonder why 8 and 9 could also be a sink and source.
9 is a sink and a source. So I call it a source because it doesn't have anything else in W3 pointing to it. And so here, so this doesn't have anything in W1 coming out of it. Oh yeah, I'm sorry. I'm stupid. Okay, so 0 is not a sink because it goes to 1. Okay, 0 is a source because nothing goes to it. Okay, 1 is not a source, but it's a sink. Okay. So I take it back. I think this is right. Within every group I've marked with S the ones that have no predecessor in the group, and with T those that have no successor in the group. And the necessary and sufficient condition for having weak components is that every T in one guy has to have an arc to every S in the next guy. And if that's the case, then every topological sort is going to have to have this guy in front of that guy, and that's the definition of weak components. Okay. So all right. So now the nice thing is then that we can find the weak components on the fly as we're discovering the strong components. We know that we discover the strong components from right to left. We first find a sink, and then we find another sink, and so on. So as we're going, we can keep track of the weak components as well. If we also do a little more work to figure out what are the sources and sinks going on. And so let's take a look at the example we just did, and imagine that I'm almost to the end, but I haven't done this KHG yet. So suppose that I'm going through this depth first search and I haven't yet learned about these three vertices. So far I found strong components here, and these, and so on. But at this point, actually, I have I have another weak component here because this guy precedes this guy, and then the rest. Okay, so at this point I have 5 weak components, not 4. But all of a sudden, in comes this new guy here, KHE, and that has that does something. So here's the strategy. We imagine that we know the strong components of the partial thing, but now in comes a new guy way at the left. I might call him -1. So I have some new strong component that's just been contributing, and I'll call him -1 for that. Now, it depends on what comes out of that strong component. The guys in that strong component can have arcs to any of these here. So we have for any subset of these 10 guys, 2 to the 10th possible abilities, we have to decide what to do. If -1 has no arcs coming out of it, or if it has an arc -1 to 0, -1 to -1 to maybe 0, 4, and 7. What do we do in each of these cases? Okay, and fortunately the rules are quite simple. If it doesn't have any arcs coming out of it, then everything collapses and we have just one weak component. But if it, I mean, let's imagine that it hits all the sources here in W1, then it's a new weak component all by itself. Because this guy, we have to see who does it go through. So if it hits all the sources in W1, then it forms a new weak component. But if it doesn't hit both 0 and 2, maybe it hits 0 but not 2. Then it's going to merge together with W1. What if it doesn't hit either 0, 1, or 2? It doesn't hit any of those vertices. But it does hit all of the sources here in here. Okay. So anyway, there are a few different cases depending on how far it goes before it comes into one of the weak components, and then we merge together some of the weak components correspondingly. And so if we keep enough stuff in our data structure that's easy to update, then we can again get the weak components on the fly as we're going through. And it turned out to be not so simple to keep everything so that it's guaranteed to be linear time in the worst case. But the algorithm, it's one of those. After you look at it, you say, yeah, that is deep. But it's also, I mean, you can get it in a day or two, but it's not like something that I would expect ChatGPT to ever figure out. Okay. All right. Okay. Any other questions?
No.
Going back to the tree that we had, is there a way to identify the weak components just based off the tree without identifying if it's a source?
Is there a way to identify weak components just from the tree?
Yeah, if you looked at the root nodes or the start of each tree and then said,
I don't think so.
Oh, okay.
Yeah, no, yeah, but you can, but this idea of sources and sinks within is sort of necessary and sufficient. So, I mean, it sort of describes the entire structure, but though I have to admit, when you start programming it, you only have to keep track of the sources. You don't have to remember the sinks. It turned out that the way you update only depends on the S's. And we learn about everything we know about the T's we can actually do without actually keeping a special data structure for that. There's a question way in the back.
So every sink in one component needs to be connected to all of the sources in the next component?
I can't hear you, sorry.
Sorry, you said every sink in one component must be connected to all of the sources in the next component? So what would happen?
Every T in W1 has to connect to every S in W2.
So what would happen if there's no link between S and
If there, yeah, there's an interesting theorem. If you have a weak component that has more than one element, it's got to have at least two sources and two sinks. And yeah, you proved that first. So there have to be two. There have to be. If it's a weak component, only one thing. Then you have one. Then it's one source, one sink in there. It's true, but every weak component that has at least two guys has always at least two sources.
In this case, if the link from 7 to 8 were removed, if that was removed, what would happen to the component?
So if 7 is removed, what?
Yeah, from 7 to 8, if you remove that,
I removed 7 to 8.
yeah.
We're going to have to collapse W2 and W3 together.
Okay, completely.
Because 7 would be incomparable with 8, and two things that are incomparable have to be in the same component. It's a tricky it's a tricky concept, and that's why the funny thing is, though, when you think of it, saying, well, these are the least you can do in order to get a total order. You think this must be something that people discovered ages ago, and so Motzkin letter said, I'm pretty sure somebody else must have noticed this, and I recommend looking at Birkhoff's book on lattice theory to see if it's in there, and we had other correspondence that Professor Tarski at Berkeley was very interested in this, and we asked me, had he ever seen this before? So nobody else had figured out this concept of weak components before, even though it seems naturally there's something tricky about it. But at the time we were doing this, we thought, well, we must be rediscovering the wheel. Yeah.
For the algorithm, is there a particular reason to keep track of the different types of arcs?
Not for this particular algorithm, but for other algorithms there are, and so if you look at several texts on graph algorithms, they will usually do it because we use depth first search also to find like dominators in graphs and all kinds. I mean, the depth first search is one of the. There's also breadth first search, but finding maximal max genes, all this stuff we use, and so in that case we. It's good to know. And when Bob first did this, he, instead of calling it a depth first force, he called it a palm tree, and he had fronds and things like this. But there was some idea of knowing, having some kind of a way to identify different kinds of edges. Arcs, yeah.
Do weak components capture all of the choices we have in a topological sort?
It covers, if you consider the intersection of all topological sorts, it says that two things are in the same weak component if and only if you can get them in both orders. In one topological sort or another. I mean, in the same strong component, you've already shrunk that to be one vertex. So this is the idea of mutual incomparability. Yeah. Hi.
So I wanted to say, first, I share your sense of amazement about Tarjan's algorithm. I vividly remember that when I learned it, it was also the first algorithm I learned that I thought, I could not have come up with this. It's really miraculous that it works. And I feel that even now, I still don't have a deep understanding of why it works. Like why a DFS tree allows you to determine this structure,
yeah,
but say a BFS tree does not.
Yeah.
Do you have a good intuitive sense of what properties a DFS tree allows you to deduce? Like, for example, can you use one to find the tri-connected components of a graph?
Okay. I kind of, I forgot to show you this book, which is Dijkstra's book. It turns out that in 1973, the same year that I learned Tarjan's algorithm in January, Dijkstra was working on. I think it was March. He sent me a draft of something that he had been working on finding the strong components of a directed graph. And he you know, Dijkstra is one of the great computer scientists of all time, and he had invented the standard algorithm for shortest paths that we talk about. He'd also had independently invented the minimum spanning tree algorithm, and he didn't read much of other people's work. He always liked to do everything by himself, but he wrote this book a couple of years later about several dozen problems that he had been working on, and explain. And the climax of his book is chapter 25, finding the maximal strong components in a directed graph, and he goes through and he describes. In his words, saying that okay, there's going to be some strong component is going to be a sink, and then we can remove it and go on and remove the next sink. And then he also has this structure, which I should have mentioned. When we formed this forest, this example was very tame. We never got into a forest with lots of branches. In general, you build a big tree, and then each one has some reason for not declaring that we have a strong component. So we can be building a rather large tree, but it turns out there is a structure, and that is if we look at the rightmost branch of the tree. Everything to the left, but we look at the rightmost branch of the tree, it turns out that the strong components of what we got so far are always obtainable by making some cuts in the rightmost branches and throw away. I mean, then the strong components are obtained like so I got, I got a tree that's going on like this, and okay, but I say that I'm currently at this point in the cave, and so I say that these guys are active. Everything that's already been declared to be a strong component, I call it settled. But then there's the inactive elements. These guys that they aren't settled yet. Okay, but all the active but at least on all the others, I know everything coming out of these guys. But the active ones, the guys on the right branch, these are the ones that I'm not sure what might be in the future. All of these guys, I haven't gotten to the end of their list of successors, and so who knows? This guy might have an arc going back here, making everything the same strong component, or maybe there's no successors whatsoever. In which case, I don't have any more strong components than. But I do have. I do have arcs that I know in here, but anyway. Anyway, Dijkstra showed that no matter what happens, there are always just a few breaks, maybe all the. But like in this case, it might turn out that so far these guys are known to be in the same strong component, because maybe I've got arc from here to here and from here to here, or something like that. But this is not in the same strong component. And these two are in the same strong component in all their descendants. So there is this nice structure theorem, and the the next strong component, well, we might get below here, and there might be a strong component here. But anyway, the way it grows, it always comes off on a fairly simple structure. But the thing we don't know is where these breaks are. We know they exist. We know there's a finite number of breaks, but it's all hidden by the complex pattern of these dotted lines that are in there. And so it turned out that Dijkstra didn't figure out Tarjan's simplification. In order to deal with this, you look at his solution. He introduced 4 new arrays that would keep track of the structure, so that he could update. So if you read Dijkstra's solution and see what his arrays are, and he thought he had solved the problem in the best possible way, but Tarjan figured out a very clever way. And okay, now, but while I was working on this section, I got into conversation with Bob again. This was 2 years ago, and we found a better way than his original algorithm. So the algorithm that I describe here is not the same one as he had in 1972, but has a different definition. His definition was linear time, but I think I got it down from 7M to 5M or something, because I didn't have to look at okay, and it was based on an idea by Reino Curcusonio and Jim Eve that they had published in in the 70s, but it turned out their article had a fallacy. It didn't work, but if you took their idea, you could still fix it up and save, make it simpler. And so. And then I spent several days in order to get this definition here is on page 9, which describes the new method that replaced the low point that Tarjan had in his algorithm, and I discuss it in this diagram and in exercise 45, which does in detail what happens. So here's a case where you learn about 1 to 2, and then 2 to 3, 3 to 4, and then 5 to 3. But these give you some difficult things, which would have been a counterexample for the method of Curcusonio and Eve. But it works when you fix it. And so I worked very hard to get this invariant to explain what low of V really means in the algorithm described here. And then we went further, Tarjan and I. We realized that if you look at it, there was actually a little bit of fat left, and we could combine 2 of the fields in one. And so here we change the definition of the simpler algorithm and make it more complicated yet faster. Now here we get to a very interesting point, and that is, here I'm saying I've got this algorithm that I love and I think is beautiful, but when you look at it, it's got these 9 steps. It doesn't look that beautiful. I mean, you can look at the code for it, and the code is really slick. It says, okay, first you look at this. If it's 0, then do this. If it's greater, then do this. And every time you want to make a decision, everything you need for that decision is right in front of you, and it's all. And we did this partly by reinventing this low pointer and make it so that it was even better than it was. And so somebody said, well, wait a minute. You had this very elegant algorithm. Now all of a sudden it's not looking so good anymore. Well, I've been quoted saying that premature optimization is the root of all evil in programming. But this was not premature optimization. This was post-mature optimization. So here we had a very mature optimized thing, and now we said, okay, now it's time for to put on our thinking cap and see if we can't squeeze a little more out, even though it might make the algorithm look a little messier. And so when the computer comes to a part of the code that it doesn't understand, it doesn't go any slower. A lot of people say, oh, you got to write your program this way because it's not so easy to understand. But the computer doesn't have. The computer is just going to follow the instructions, and it's going to go faster if even if it's I remember reading a review once. The guy was saying, if I caught any, somebody had written a paper about a certain algorithm, and the reviewer said, if I caught any of my employees using a trick like this, I'd fire them. And so immediately I went to the literature and looked up that article because I wanted to know what it was, because it is possible to use trickery when it's well documented, but trickery can also be terrible if in some cases where the program's going to have to be maintained by somebody else, and they aren't going to understand the subtlety. So you have to document it when things are subtle, but that doesn't mean you can't use subtlety. One other thing we added to this algorithm is a recognition that in many cases you can stop when you know that everything. You don't have to look at all the edges of the graph, because if you get to a point where you've already seen every vertex, and you know that all of the vertices in the tree you have are in the same strong component, then you don't have to look any further. Okay, so I guess she's giving me a hint that we're.
No, we'll turn it back on.
Oh, I see. Okay. Right. Well. So I think it's interesting that Dijkstra thought about this hard and didn't see the secret sauce to define the low point. But you still have the feeling that ought to be. So as I mentioned in then Bob Tarjan and Uri Zwick went back and revisited it, and they came up with their new version of it and put it on archive a couple years ago, and this is mine, and I think it's worth spending some time studying the code. So the other thing I wanted to show you is the code. So I've got, I left one of these in the, okay, so I've got implementation in CWeb of the algorithms, and it's online. What? Oh, you want to zoom? Okay, so I have a program called Tarjan Strong and Weak, and I have another program just called Tarjan Strong. You can play with it, and it has debugging stuff, and you can watch what it's doing. Do you have a question? Yeah.
Did you know Dijkstra personally?
Oh yeah. His strength was his inability to compromise, and it was the kind of thing where people wanted to have his advice, but they were afraid to have him as a colleague because he was very much perfection. It was, I mean, like, I visited him at his home in Netherlands also, but then he lived in Austin, Texas for a while. And, you know, we would play four hands piano together, and I would always let him lead, you know. But he was kind of like an encyclopedia. Whatever we were talking about, he would know more about it than I did. Discussion, but the last years of his life, he stopped writing computer programs. I thought that was really dumb. He thought it was better just to do everything with pencil and paper. So,
is this C-Web program on your website?
Yeah.
Is this C-Web program up on your website?
The C-Web programs, yeah, but I'm going to make them easier to find.
Okay.
I looked today, and they hadn't been updated since 2022, and so I'm going to fix them. By the weekend, they'll all be in great shape. And I'm also going to put up I mean, the input is in the form of a graph in the Stanford graph-based format, the SGB format. By the way, I wrote up Tarjan's original algorithm in this book, which came out in the 90s. And so one of the chapters is about strong components. Can you see that? And so one of the demonstration programs in Stanford graph-based is we have a directed graph that has about 1,000 vertices. Each vertex is one of the categories in Roget's original thesaurus from 1820 or something like this. And so, you know, category 5 might be angel, and or I don't know. Anyway, the categories. I don't have an example here, but it was interesting to see what the strong components were from Roget's thesaurus. You know, A goes to B if B is a synonym of A or an antonym of A. But then so three things are clustered if you can get, you know, if you can get from any one in the component to any other, and it's interesting to run the program and see what those components are. Okay. So this describes the original algorithm, and also the programs print out not only the strong components and weak components, but also they give a subset of the arcs, which are enough to define exactly the same strong components. So you can take a directed graph and remove a bunch of the arcs, and it doesn't affect the strong components. And so this gives you a subset of arcs. Well, there's so much more to be said, but I hope I explain why I put a lot of time into it, because it was fun learning all this stuff.
Should we end it there? You'll stick around a little bit for the. So thank you everyone for joining us.